Welcome. Today we're going to talk about vector fields. So what is a vector field? So in 2D, it's just a vector function. It goes from, has an input in R2, I'm going to call it F, and has an input in R2, and it has an output that's also in R2. So it's a two-dimensional to two-dimensional function. So something like this. Write it down, and we can write it as x comma y. So that's a two-dimensional input, and it has some sort of output that's two other functions inside, f1 and f2, x1, x and y. So there's your vector function. So we've seen these before in this class, but now we're going to formalize this idea of a vector field. So there's many different types of vector fields. We can think of a few examples. So one example would be a velocity field. So these are like, if I were to draw a little two-dimensional plane here, there's your x and there's your y. And then if you think of every point in the plane, we put in our value x and y, and we put it to both of those, and it dictates some vector emanating from that point, x comma y. And if I pick a different point in the plane, x comma y, some other point, maybe you get another vector coming out that's like this. So every point in the plane I can put some sort of vector. And so I'm just giving a few example points, and you could draw as many as you like. So a velocity field would be an example of where these vectors then would be indicating some sort of flow or velocity. For instance, wind. A wind plot over the surface of the Earth, or some little patch of land on the Earth. Okay, so these things aren't just abstractions. They're very real. They're modeled all the time. So for instance, I actually pulled one up. This is the Mesonet observations for Salt Lake City. So here is a plot here of all the wind sensors in the valley. We also have some in the mountains here, and they have these little hockey sticks right there, and the tail end where the little where you'd hit the puck, that's the end where the wind is coming from, and the long handle of the hockey stick tells you where the wind is going. So for instance, right here at on the 215 and I-15 intersection, there's a wind sensor there, a little fan that detects the wind, and it's saying that wind is going about 3 miles per hour in a south-southwest direction. Likewise, if I'm out here in West Valley City, there's some other out here in West Valley City, there's some other one that's going in a southwesterly direction at 2 miles per hour on average. Of course, if you get along the benches, you see the wind here is going completely in a southerly direction. So this valley gets a lot of swirling winds. So obviously the winds tonight that I'm recording this are pretty low. However, up in the mountains you have strong westerly winds going on the order of 30 miles an hour. So of course very different plots. But now the vectors here, you can think of them as vectors. It's just there's a strength to the wind and also a direction to the wind. And so this is an example of a vector field and very much in the real world. So we're talking about a two-dimensional plot of it because while the wind, of course, is flowing in 3 dimensions over the surface of the Earth, we're only measuring it close to the ground. We're thinking about only wind currents going close to the ground. So we can think of it as a two-dimensional plot, a vector field. So obviously these can be very complex and very interesting. And of course, along with this is So I'm going to take this away like that. So another thing we can think about here is, so the wind plots are one example of a velocity field. You can think of others like any kind of fluid flowing through a surface would be an example. Let's just now, so there's some real world examples where there's actual data involved. Let's go back to some equations. So let's just do an example. We'll try f x comma y is equal to, we'll just make a function that we'll call this y negative x. So I'd like to get a feel for just plotting these things. So I'm going to make a little Cartesian coordinate system. And then there's I'll put 1, 2, 3, 1, 2, 3. All right, so let's try a few example values. So let's try the point 1, 0. So we always have to keep track of our x's and our y's, both the position on the plane and the direction which the vector is heading. So we have to put in for x 1, negative 1, and a 0 for y. So that's 0, negative 1. So that means the vector is pointing in a fully downward direction. Right? So again, we have to juggle lots of pieces of information. The input here tells you where the vector is emanating from, and the vector here tells you the direction that it's going from. Okay? All right, so it's not telling you a point on the plane. It's telling you the direction it's emanating from the position here. Okay? So there's some subtlety here. Once you get the hang of it, it's no big deal. Let's try another one. We'll try 0, 1. All right, we're going to try up on the y-axis, so right here. All right, so again, we're going to put in 0 for x and a 1 for y. And now that is a vector pointing completely in the rightward direction. So it's going like that. Okay, all right. So these have magnitude 1, unit magnitude, both of them do. But we don't really, because we're in the plane, and obviously this is a measurement, this is a unit length of 1, the vectors don't necessarily have to have that same length of measurement. We usually draw them in some sort of, we scale them so that they're appropriately sized for what we need to see. So the actual length of the vector when you draw it doesn't have to be measured exactly. It just has to be, all you have to really know is the relative magnitude. So we'll get into an example of that. So let's talk about then, of course. Now let's try another point. We'll go in the negative 2 direction. So we'll try negative 2, 0. All right, so that becomes, okay, we put in a negative 2 for x, and that becomes a negative, and negative 2 becomes negative of negative is a positive, and 0 for y again. So now again, so we're over here. That's the position our vector is going to be emanating from. And we're not going to go anything in the horizontal direction, but we're going to go 2 units in the upward direction. So again, I don't have to measure on here actually 2 places, but I do have to make it, roughly twice as long to make it twice as long as whatever my reference vector length is here. So I'll just make it look about twice as long. It turns out that that's pretty much 2, but with my length scale, but no worries. All right, so what we're seeing here is as I'm getting further away from the origin, the vectors are getting bigger. And clearly if I put in here, if I take this point and I make that a 3, 0, that will be a 0, negative 3. So that's even bigger than before. So that's going like that, okay? And of course we can start, so there's 2, and there's negative 3, and that would also have that look there. 1, 2, 3, like that. And we start to get a handle for what's going on here. Sorry, that should be out there, and that's all the way to 4. And that'll be a length of 4 there. And so on and so forth. So we see that there's some swirling going on here. Now if I pick a point, let's say there's 1, 1, we'll go with 2, 2. So if I go 2, 2, that point right there, of course I'll be going in the 2 and -2 direction. And that's going to go at a diagonal like that. And so you can see there's a similar diagonal going there and a similar diagonal going there. So we see that there, if I were to drop a leaf in this plot of, if this were a wind plot of all the wind going on the surface of some region of our space, some sort of fluid flow, what we're going to see is some sort of circular path, right? And it seems like the velocity of the wind is going to be going faster and faster, but it's always going to be swirling around like that. Okay, so there's just an example of a velocity field or some sort of vector field. All right, so let's talk about some other physical examples. So one classic is a gravitational field. All right, so here, remember that the force of gravity so we'll call that, I guess we'll just call it F. That's going to be equal to the gravitational constant times two masses. The first is a lowercase mass, a smaller mass. We usually think of it, and there's another mass. It's the bigger mass. And it's proportional, or it's equal to the product of the two masses times the gravitational constant, all over the length between the two. So if I have a big mass here, and a little mass here, and the length between is what I'll call R, like that, then the force attracting is going to be the magnitude of that force, I should say, attracting towards the bigger mass is going to be equal to that. So now what we'd like to do is actually put these masses in three-dimensional space, and actually these two masses, so this one we'll consider just at the origin, so I'm going to draw that again. Here's our, I'm going to make it in 3D. So I have a big mass there, and some little mass out there. So this is going to be at the origin, 0, 0, and this will be somewhere else. And I'm going to call that position x, the vector. It'll be x1, x2, x3. Okay, and so I want to know how to express the force. We know that it's going to be a force going that way, so I want to be able to express. So if I have another mass that's over there, if the mass moves and I put the mass over there, the vector is going to be pointing again in towards the origin. So likewise over there. Everywhere I put the mass, so I have to come up with a force field or a gravitational field, x1, x2, x3, that will always produce these vectors and have the appropriate length, i.e. that they're going to have this length right here, and they're going to have a direction determined by this sort of always radially pointing inward. So how do we do that? Well, we know that the magnitude of the vector has to be g little m, big M, all over r squared. What is the distance here? Well, that's going to be the magnitude, the vector magnitude, right there, from the origin all the way out there. So that represents what I'll call r, so I can put that down there and make it squared, right? Right, so that is the magnitude of the vector, and then I need the actual direction. So what's going to be the direction? I'm going to put a question mark there. So the direction we know has to be pointing in towards the origin. So we already know the vector pointing that way, and that's actually just x. It's pointing this way, right? So we just need to flip it and make it go the other way, right? So that's, of course, going to be negative x, right? But we don't care about the magnitude of this vector. We just want its direction. So what we do is we make it a unit vector. And what we do is we say negative x, so that's the direction going that way. But because we don't want its magnitude, we divide by the length of the vector. So now this vector has a unit length, or a length of 1. So putting those things together, taking it at all, we see that our force field vector, our gravitational field, will be G M, capital M, all over x. So we had a power of 2 there, and now I'm going to add another power, so it's going to be a power of 3, and then what we're going to do is make it negative and put the direction will be this. So this right here is a scalar, and this is the vector part, all right? So that creates this vector field. So any point here it's going to create all these vectors in the entire three-dimensional space that are all pointing towards the origin. And so the reason this works is because the origin, and of course, is where the mass is located. So we could do another example. Let's say if we have a mass at some point, a mass, I'll call it capital M again, at a point at a non-origin. So how would I make my gravitational field then? Well, okay, so if my mass is at the point, let's call it ABC, that's the point in space, so maybe it's right here, ABC. Right, so so if I have this here's my coordinate system, my Cartesian coordinate system. I have this point ABC. Right, so now I want my force field to always attract there. That's how I want my force field to look. If I have another mass, here's the big mass. If I have some other mass here, and typically, right, as we get further away from a mass, the gravitational pull should be less and less, right? So I make the vectors a little shorter. How do I model this, right? So now we're not going towards the origin. Well, what we always do is, anytime I want to make a vector that goes between two vectors, I just have to. So I'm going to say that's my x vector, and that's what I'll call my a vector, which is just the a, b, and c numbers. So what I have to do then is, so that's what I'll call this, a. All right. So how do I create this thing? Well, then I define r is actually going to be the distance between the two vectors, or the two masses is going to be, the length of that distance is going to be a minus x, right? If I want to create a vector that's between 2 points, I simply subtract. It's vector subtraction. So that becomes my r. And likewise, what I do then is my force field, the resulting force field, x1, x2, x3, and I'll put a little subscript a down there to indicate that, and it's going to be G, little m, big M, all over a minus x to the third times a minus x. All right, so is this the right, do I need to make it x minus a or a minus x? Well, again, I want it emanating from x, and I want it going towards a. because I'm talking about the force of gravitation that's produced from that's being experienced by this little mass out here at x. And so that truly is the right way to go, this direction. So we want that minus sign attached to the x and not the a. So there's an example of how to move things around and get used to vector fields. So again, now all the vectors are pointing towards A and not the origin. Okay, so let's talk about another example real quick. Electric fields. And we have, I usually use the E, and again we're talking about some points in three-dimensional space. And usually what we indicate, we use what's called the electrostatic force, which is going to be epsilon, which is the permittivity of free space. You can look up what that constant is in any physics book, times charge of some charged particle, times some other charge, a bigger charge. So this looks a lot like gravitation. It's the same basic rule as gravitation, except for we've changed constants there. G, and these aren't masses anymore, but charges, they're coulombs. And that's going to be squared. All right, and then what we do is that's going to be to the third power, be negative. So it's the same sort of thing. We don't actually put that negative sign there because what happens is, right, so if Q is let's say a negative charge, and big Q is going to be a positive charge, and we have something like this, then there's an attraction. And so what we do is we actually make this a sign thing. So Q actually has a negative sign associated with it, and that makes sure that the vector always points that direction. However, if Q is a positive charge, then you'd expect the force field to go the other way, because we're going to have repelling. The two positive charges will repel each other. So that's if we have plus. This is if we have a minus Q, and this is if we have a plus Q. Okay, so whichever one, you get those sort of behaviors coming out of it. All right, so so finally we want to talk about is another special class of vector fields. So we want to talk about a special class of vector fields. And we're going to use these types a lot in this class, which is called a gradient field. So if I have some function f, a scalar function, x comma y comma z, right? So it's a scalar function. So it's going to, the inputs will be R3, and the outputs will be just single real valued. Okay, that's a colon there. All right, so this scalar field then, if I then create a vector field by taking the gradient of f. So let's remind ourselves what the gradient is. It's going to be df dx, df dy, and df dz. All right, and sometimes we also write it just as fx, fy, and fc, the subscript notation for derivatives. All right, so this is called a gradient field. So we take a scalar function, any scalar function we can, and we create a vector function by just listing off the derivatives of that single function. So f is the same in each one of these, but we've taken each respective derivative and give it its own dimension. So these sort of vector fields are really important. In fact, they're also called conservative vector fields. And so let's talk about an example we've already seen. Let's go back to gravitation. It turns out it's a conservative vector field, and we'll see why. So we have this function f. We said it was equal to g little m, big M, all over. Like that. Okay? So let's write out what this looks like fully. All right, so we have a G, little m, big M, negative sign. So what's this thing look like? That's going to be an x1 squared plus x2 squared plus x3 squared, all to the 3/2 power. And that's going to be the denominator, and we're going to have a negative x1. Likewise, we'll have a negative x2 with the same denominator down there, ditto, and a negative x3 with the same denominator. Okay. So with that thing then, I'm looking at this. I want to find out, is there an f such that the gradient of f is equal to our, what I'll call this, the gravitational field. Is it equal to this? All right, so we want to look at this. We want to see is, if that function's fx, and that's equal to, we'll call it fx1, Alright, so what we want to do then is actually just take the antiderivative. We want to find out what the antiderivative is of this thing, and it's pretty clear that once you do the calculus on it, that this is equal to and that's of course just the function 1 over the length of the function. So that's a scalar. We can also call that 1 over r by our notation before. So the function f of x1, x2, x3 is equal to 1 over root x1 plus x2 squared plus x3 squared. This function is what I call the gravitational potential. So sometimes they talk about this potential. So we usually talk about, if we have a gradient field, gradient of f, we sometimes talk about f as being the potential. And we'll see later on in this course that these gradient fields are incredibly important, and they're found all over the place, and they end up being very useful. They have a lot of nice properties, which we'll get to in due time. So thank you very much.